Good morning, everyone. My name is Wang. I'm from the AstraZeneca. It is very honored to be invited here to present some of my works in the AstraZeneca by using these AFA technologies. So today I will talk about some of the outline here. First is overview of the AFA and dry pulverizations, and then we'll also talk about experimental design and results of the two sample preparation workflows comparisons, which including the protein extraction by tissue type, demonstrate the consistency and efficiency of extraction. We also include the variance in protein abundances determined by the mass spec, which demonstrate the data quality. And finally, we will go to the conclusions. So first, I will briefly introduce the two instruments that our labs have. So the top one is CP02 cryoprep dry pulverizer. It's used mechanical force to cryo fracture flash frozen tissues. So it helps to disrupt ECM and increase the surface area, increasing the efficiency of the lysis buffer. And this bottom one is we use LE220RSC focused ultrasonicator. This is we used for our proteomics for the homogenization part. I won't go through very details of the cores of the parameters, but we do use these three very important parameters to optimize our workflow and increase our data quality. So the first one here is called the peak incident power, PIP, which is the maximum amplitude of the acoustic energy applied to the sample row. And also we have another parameter to tune is the duty factors, which is percentage of the process time that is active AFA interrogation, and also the cycles per burst. It is a number of the acoustic pulse during each on phase. So we anticipate optimize of these three parameters to increase the protein extraction completeness, which we think which we will further improve our data quality. So our motivation and goals for this method development is first to optimize AFA parameters to maximize protein extraction and decrease the variance across the different tissue types. And also we want to demonstrate improved the data quality with two different workflows with dry pulverization and without dry pulverizations. So this is our current experimental design for the tissue sample preparations. So we basically just weigh the tissue in this tissue bag, and we do the dry pulverizations with cryo prep and do homogenizations by the AFA treatment. And the further we do after the protein has been extracted, we do some quantification which measure the protein concentration, and then we do the sample preparation for global proteomics, and we can, based on these two metrics, we use to evaluate pulverization and AFA parameters. So here I want to use, so this workflow can be in our lab to use different types of tissues, including the liver, brain, kidney, heart, pancreas, intestine, and spleen. And so here I will give the briefly examples. For example, for the livers, first we collected the about 15 to 15 milligram of the sample and insert the tissues in the middle of the tissue bag. Then we flash the sample, flash free the samples. So we submerge the bags into the liquid nitrogen, and we do the dry pulverizations to make sure its frozen tissue become the powder. And because it's 1 ml of the tube, so we add the full 1 ml of the lysis buffer before the homogenizations, and we do the denaturation, 95 denaturations, and do the AFA treatment to make sure all the tissues has been homogenized. And we do another round of the denaturation and spin them down, And so we can see that basically there's nothing tissue left. Then we do transfer the supernatant and start to measure the BCA, and then further do the global proteomics work. So when we first start to use AFA technology, we needed to first figure out to set up a baseline. So in the beginning, we start with get a reference from the recommendations for TPX stripped protocol. So which this is the parameters we're basically start with. The volume is 1 mil, 1 mil because it's a 1 mil tube. And so the PIP we start with 150, which these numbers is corresponding to the single sample treatment. So not the distributed power of the PIP for the multiple sample treatment. And we use the duty factor is 25, and CPB is 200, and the duration is 5 minutes, which also applied to the whole row, not of single samples. So after we do the homogenization, our next step is to measure the protein concentration, and we get around 2 to 3 milligram per milliliter of the protein concentration. And we have 2 scientists to also do the global proteomics sample preparation. CV is getting from 25% to the 48%, which is not good. It's not ideal for us. So our next step is try to do the several rounds of the optimization to make sure we get a very maximum efficient protein concentration. So our final version 4, gave us really good the protein concentration, which about like 6 mil per mil compared to the version 1 and also bead beatings, which gave us about like 2 to 4 milligram per milliliter. The version 4 gave us really maximum and very good the protein extractions. And also we compared the identification of the protein. We also see the increased identification on the version 4. And also we compared of the CV, there's variance. The version 4 gave us more precise data compared to the bead mill and AFA version 1. So it gave us really good data quality based on this condition. So this version 4 is 450 for the PIP and 50 the duty factors, and the CPB is 1000. And we also, here we use 2 different dithering. I want to show, how can I show the videos here? Yeah, we wanted to show that the Y, we also including the Y dithering and Z dithering. So the Y dithering is a horizontal movement, and Y is a horizontal, and Z dithering is vertical. So we give them a thorough environment to make sure the samples are fully homogenized. So that's gave us really good to make sure we can get a really good data quality. And we also apply this technology to all the other tissue types, including the heart, kidney, liver, the spleen, and brain. We find that the protein concentration, also we can get really about like 4 to 6 milligram per milliliter of the concentration. And also the variance is give us about like 6% to 20%, and 6 of 7 tissues the tested falling below the 20%. So this high efficient extraction and quality of the data across a wide range of the tissue hardness suggests the developed method is broadly applicable. And then I summarize this workflow 1. It is very good. It gave us a really good protein extraction and also low variance across the replicates. So it is this workflow is very good for 24 samples for 1 cycle homogenization. So if you have a small sample size, it's very good to use this workflow, give you a really precise data quality. And if you have like a lot of samples, like more than 96 samples, and then we also have another workflow to develop, and then can help you to proceed the sample preparation very faster. So here the workflow 2 is more high throughput workflow to make sure that we can proceed to the sample preparation very fast. So we kind of like remove these dry pulverization, these steps, so we can skip these steps to make the preparation very fast. So here I make the comparison. So if you see these two graphs, workflow 1 is we basically use a large size of the sample, the tissue samples, about 15 to 50 milligram. And if you use a high throughput 96 samples, then you're gonna use like about a less mass range is about less than 10 milligram, around like 5 to 7 milligram, which is preferred. And we do, and for the workflow 1, which is we use 24 samples, and it's good for one cycle. It's good for one cycle for 24 samples. But we need a pulverization. And for the high throughput, we don't need the pulverization, and it's good for 96 samples for one cycle homogenization. Then I just make the summary of these two, the workflow. So the first one, the workflow 1, we just need a large size of samples. I just want to emphasize that we need a large size of samples, and we need the liquid nitrogen to flash the flash-free samples, and we do these powders, and we do the homogenizations. And with high throughput, the only thing we need is to get the tissue samples, and we directly on the covars for the homogenizations. And after we spin them down, we can see no tissue left in these tubes. So then a lot of people may have concern how it's easier to get of these. Before that, I would just want to talk about the data that I wanted to introduce, how the data quality. So here is like I test with heart and the liver and kidney. So we see that we get a pretty good like protein concentration with about 6 to 8 milligram per milliliters. So we use the version 4 of the parameters. And according to the tissue hardness, for the softness, the tissues will get a really precise data. It gave us 8% of the CV. And if you and then you can see that when the change of the tissue hardness, we get a little bit higher of the CV, but it's still falling below the 20%, which gave us really good quality too. And you see like after homogenization, we don't see the tissue left. So that's one. Then we think about like another concerns is how you can really cut this small piece of tissues without using the knife, and also give us replicates very consistent the similar mass. So we also try to use this biopsy punch for the fresh frozen tissues. So this is from the Integra. It has a different diameters of the biopsy punch from the 1 millimeter to the 3 millimeter. So I tested with 1.5 and 1 millimeter, and also tested with 2, but I won't talk about the 2 because it's out of the range here. So I used the 1 millimeters with plungers, and which gave us about 7 to 9 milligram of the tissue per punch. So it also depends on the thickness of the tissue bulk tissue that the project team gave us. So based on what they gave us, normally they give us about like more than 100 milligram. So though we can use 1.5 millimeters of the plunk, and then to get about 7 to 9 milligram of the tissue. Also, you can use the 1 millimeter of the plungers, which give you even less if you need to. Even can be used to use the TPX strips for 96 samples if you want to really use a really tiny small amount of the tissue. By the way, this also depends on thickness of the tissue. If you have a tiny slice of the big tissues, based on this tissue, you will get a less piece. So I also want to show these videos that how I do the get the small piece of tissue. I twist with a biopsy punch, and which gave the sample will be in the needles, and we just inject the samples from the needles to the tubes. Then you will see the tissues will be in the tubes, and it will be easier for us. You don't need to weigh them. You just need to put each of the biopsy punch to each samples. It will be very fast to get the large size of samples. And then, so in order to, for this, you can choose proper rate plungers selected based on your preferred the tissue weight. So for here, what I've talked about like here is for heart, kidney, and liver, I used 1.5 millimeter of with plunger. So final give us a 7 to 9 milligram, the tissue in the 120 lysis buffer. And then I also test with a spleen, which I show here, the data, the spleen and small intestine, and I use 1 millimeter with plunger, which gave us a final weight about 2 to 4 milligram, and in the 120 lysis buffer. So here I want to show that the spleen and intestine, the protein concentration is pretty good according to the small size of the tissue mass. It gave us about like 3 to 4. 3 to 4. Here is a little outlier because I cut a really tiny piece, probably around the 2 milligrams. So it's going to give us a little bit, like you see, it's not variability. It's just like the too small piece of the tissues. So so you can see intestine I cut very consistent because consistent. So it's pretty much very. You see that's protein concentration is very consistent. And here is this. We just test with global proteomics for the variance. The CV is also pretty good, around 10%. So based on that, so this both of the workflow gave us really good the protein extraction and also data quality. So here in the conclusions, we finally achieve our aims and also can deliver our data to our project team. So we first optimize these AFA parameters to maximize the extraction and also decrease the variance across the different tissue types. And we also demonstrate improved data quality with and without dry pulverization, sample processing, workflow tissue. And we get the CV percent be 9 to 15%. So if you have like really hard tissues, it might get a little bit higher variance. But for the soft tissue, it's pretty precise to the less than 10%. And if you have a small size of samples, workflow 1 is good for 24 samples. But if you have really large size of samples, then you can choose the workflow 2, give you a very high throughput. The 96 samples also save you a lot of time. So I think that's all my talks today. So any questions?